Let me thank Alvaro and Peter and the rest of our organizers for this nice conference. It's very nice to be back in Cape Town. As you probably know, I was postdoc here and I spent great time, so it's always good to visit Cape Town again. Well, so I'm going to talk about following a little bit Marian's talk and also Karsten van den Broek talk this morning. You will see later what. I'm going to talk about future cosmological singularities. I will focus on some theoretical aspects that we've been dealing with along the year, and also how possible a universe that may end in a singularity is according to background observations. These are based in these nice works that I recommend you to read, made also with the chairman on this session. So this is the summary of my talk. Well, I will just start with a brief review about Freeman Professor Walker cosmology, then just another brief review about what we understand about singularities in general relativity, the classification that has been provided in the last years about future singularities in cosmology. Actually, Marian gave already this classification, so we will pass very quickly. Then how singularities appear in dark energy models and modified gravities. And then, I will start to talk about what is new in this work that we published recently. That is what we have called Q-singularity. That's basically a way to understand the rest of the singularities, as we will see. And then I will focus on how variable are these models, these singular models, in comparison with the observations that we have. So, Freeman-Robinson Walker cosmologies, as you all know, we need some kind of fluid that does not fulfill the energy conditions in order to get late time acceleration. In this sense, as has been widely analyzed in the literature in the last almost now 20 years, time goes very fast. Well, a lot of models have been proposed in order to describe this anomalous behavior of the universe expansion, and according to what kind of model you introduce, you may have one behavior or another. However, depending on the behavior that you may introduce in your dark energy or modified gravity, you may have a universe that ends in a singularity. But before that, let me review what we understand about by a singularity in general relativity. Well, according to the Hawking and Ellis theorem, what we understand by a singularity is when we have a space-time where geodesics ends at some point of the space-time. So geodesics are not complete. However, this doesn't mean that we may not have a violent event at that point. We may have completeness in the geodesic equation, but we may have a divergence in the tidal forces. In order to know what may happen, it is very useful to calculate the integrals proposed by Tipler and Kroller that are going to tell you if the tidal forces and the separation between infinitesimal geodesics are is gonna diverge or not. So, according to that, we can classify the singularities in cosmology, as Marian did in her previous talk. According to this, what we have is that actually the only real singularity in the sense of geodesic incompleteness is the big Greek singularity, where you have the divergence of the scale factor that consequently affects to the Hubble ratio. Then we have the Saez singularity that has been also very widely studied in the literature, as we will see later why. And these other, well, type 3, type 4, that basically generalize the previous one. And recently, recently, in 2009, not so recently, another singularity was analyzed where the equation of state for dark energy diverges. This may have some consequence, as provided in this paper by Dabrowski, when you study even the background evolution. And what we found recently is that we may have another kind of singularity that affects not the equation of state directly, but its third derivative. This may have no consequence at the background level, but this may affect the speed of sound for dark energy, because it depends directly on the first derivative of the equation of state when this depends on time, obviously. The important point is that when you deal with interacting dark energy, dark matter models, all these singularities may be the consequence of just a single one that we have called Q-singularity. Basically, the interacting term in all these cases, when you have any of these cases within the framework of interacting dark energy, dark matter models, you are going to have that interaction, the flux between dark energy and dark matter is going to diverge. That's why if you look at this point in the opposite way, you will conclude that all the singularities are just in this framework, as I said, all the singularities are just the consequence of the divergence of the interacting term between the dark components. But before showing how the Q-singularity may be, let me just briefly review how singularities appear in cosmology. Well, the simplest model that was proposed a long time ago, and this is just an example. It's just a scalar field where you don't have a canonical kinetic term. In this case, there's a minimally coupled scalar field. When you have the kinetic term with the opposite sign, so a negative kinetic term, you are gonna end with the first derivative of the Hubble parameter being positive when the scalar field dominates, and this will end in a big Greek singularity in this case. This also happens when you deal with some F(r) gravities. Actually, what is very interesting to see is that those F(r) gravities which accomplish the chameleon model that some talks in this conference have been talking about, you have that all these models, due to the chameleon mechanisms at the cosmological scales, may show a sudden singularity. The point found for the first time in this paper by Frolov is that you have a potential that's contains several critical points, and one of these critical points is a sudden singularity, as you can see when you deal with the phase diagrams of of these models in the scalar tensor picture. What you find there is that you have an asymptotically stable de Sitter point, but at the same time you have also an asymptotically stable point that is actually a singularity, a sudden singularity. So, well, after this brief review about singularities, let me start what we did in this paper with Jose and other people. Well, when you have basically, let us just focus in a very basic model with an interaction between dark matter and dark energy. Just forget about the background theory behind this interaction. And when you have these kind of models, and just by combining the equation, what you get is that the interaction, the flux between dark energy and dark matter, is gonna depend on the Hubble rate and the derivatives of this, as well as the equation of state parameter for dark energy. The point, the main point basically is that depending on how this term, this Q term is, you may induce a future singularity in your background evolution. And you can easily see this by, well, assuming a general answer where, depending on the parameters writing here for the Hubble parameter, this alpha and this b, this Hubble parameter is going to contain one singularity or another. And basically, when you have that the Q term diverges, it means that you are going to have, depending on this alpha, you are going to have one singularity or another. Just to show those two examples, if we have alpha equal -1, basically you are going to have a big grid, and the Q term is going to diverge. And in the same way, when you have alpha between -1 and 0, you have that at a finite time, the Hubble rate is gonna diverge, however, not the scale factor, and you are gonna have a big freeze at the same time that you have a divergence in the interaction between dark energy and dark matter. When you, well, these are just two another cases where you have a sudden singularity and a generalized sudden singularity. The interesting point that we found is that in addition to the singularities, cosmological singularities that have been analyzed in the literature before, you may have that when the dark energy equation of state depends on time, that is maybe described by just a scalar field, a vector field, or almost every dark energy model besides lambda CDM depends on time. The equation of state depends on time. And what we found is that in the case that you have an equation of state that may diverge, whose first derivative may diverge, there is a new singularity that may not affect the background evolution, surprisingly, but will affect the perturbation. Well, will affect the universe evolution at the perturbation level. This is interesting. It's something that we are currently exploring and thinking about. But it's one of the main points that in this new singularity, in the interaction term between dark energy and dark matter, provides. Just analyzing one example that has been widely studied in the literature, when you consider an interacting term that is proportional to the dark energy density, something that has been, as I say, widely explored in the literature, you have that, well, the interaction term is going to be, can be rewritten in this way, just in terms of the Hubble parameter and the first derivative. So, by a first look to this expression, one finds that obviously if a singularity, a feature singularity exists and the Q term diverges, this is gonna induce as a big rip or a sudden singularity. So analyzing this case just for this choice of the parameters, where surprisingly the equation of state parameters for dark energy, in this case constant, is not less than -1, you may have, actually you have, for all the trajectories in the phase space, you have that for all the trajectories that leads to an expanding universe, I have to say, you will have, except for the green one that represents the dark matter dominated universe that is unstable, you will have that this universe is going to end in a big rip singularity. This is interesting because, in spite of that, the equation of states for dark energy is not phantom, is not less than -1. You may have that a big rip singularity occurs due to the interaction between dark matter and dark energy. However, well, this may be interesting from the theoretical point of view. You see that in this framework, in this cosmological framework, you may have that all the singularities are just the consequence of the divergence in the flux of dark energy and dark matter. However, what happens with these models? Are they related, or are they not? And for doing so, we proposed some months ago, actually before studying the occurrence of this Q-singularity, we proposed some parametrizations of the Hubble parameter that accomplish each singularity of our classification, the main ones, the big rip, the big freeze, the sudden singularity, the generalized sudden singularity. And by using, well, some background data, supernova data, Hubble parameter from early type galaxies, and BAO, together with a prior on the Hubble parameter, and applying the technique of minimizing the chi-square, what we found is that the first two models that we were studying, where A represents a big rip singularity and B represents a type 3 singularity, well, they give these values for the best fit. And the most interesting point is that using the Bayesian evidence and the Jeffreys scale, these models are so good statistically as well, are so good. We could say that lambda CN is not much better than them. What is important, especially because in both of them, depending, that's true, on the prior that we use on this, on one of the three parameters that we have, the one that actually controls where the singularity occurs, so the singularity time or rip time. It's true that our analysis depends on the prior that one assumes on this free parameter, that was not so trivial, as this parameter may go from the present time to infinity, as well, basically when you asymptotically move the rip time to infinity, you are going to recover lambda CDM somehow. And the important point is that analyzing this when assuming a uniform prior and a logarithmic prior, while in the case of the of model A that represents a big rip, you have that the one sigma region, when assuming a logarithmic prior that's according to the numerics that we did, what was more suitable for this. While in the case of model A, what you have is just a lower bound, that is the usual numbers that people have been obtained when comparing these singular models. Usually you obtain just a lower bound, so the singularity can occur any time from that lower value, what means that basically it may never occur. The point is that for model B, that is according also to the Bayesian evidence that you have here, can be compared statistically with lambda CDM. The important point is that this model, it gives you, using the data that I showed before, BAO and supernova data and Hubble, the data from the Hubble parameter, you have that at the one sigma region, you have a finite value for the rip time. This can be seen easily when showing the contour plots. Here you have the rip time normalized with respect to the age of the universe. And you see that while in the case of model A, that represents a big rip singularity, the logarithmic prior on this parameter gives you that's what an infinite time for the rip time is as possible as a finite time. In the model B, this is not the case, and the important point is that at the end we may think that both models are possible well, from the statistical point of view when comparing with lambda CDM. Just comparing how the models behave in comparison with lambda CDM. Lambda CDM is this value here, is this line, the gray line. We have that basically, as expected, all the models more or less agree in the past, independently on the prior that we use on the rip time, while obviously in future they are gonna have a very different behaviors. Well, just let me conclude. So, as I showed, we may have that all the singularities that people have been studying in the literature are the consequence of a single one, that when you deal with interacting dark energy dark matter models. Actually, this new singularity may induce this singularity may induce a new one that affects the derivative of the equation of state for dark energy and consequently the speed of sound. Two of the parametrizations that we were dealing with are as good as lambda CDM model according to Jeffrey's scale, so we cannot discard them in comparison with lambda CDM. And also the other important result is that the lower bound that we found, the lowest one, is about 1.2 to 1.5 times the age of the universe, what means basically about 2.8 billion years before the singularity. So we can say that in any case we are safe. Well, that's all. Thank you very much.
You say these two parameterizations are as good as lambda CDM. Do you have a Bayesian evidence computed value to compare this?
Yeah, well, basically we say that they are as good as lambda. Well, maybe I'm very optimistic. Better say, they cannot be discard in comparison with lambda CDM model because according to the Bayesian evidence, this quantity here that is normalized to lambda CDM to 1, so that we can compare with the rest of the models. According to the Jeffreys scale, it says that you cannot discard a model if the comparison is less than 1. Because statistically you are not so powerful to favor one of these models. Even if the chi-square or the reduced chi-square is smaller than in the case of this model.
I have two questions. One, you said at some point that the equation of state will be smaller than minus 1 of the singularity.
Yeah.
What is the effective value of that equation of state?
Yeah, exactly. It's
So
less than minus 1.
The interaction.
Yeah, the question is that when you add an interaction of this kind, of this type, you are going to have that the effective equation of state for dark energy is not WDE. It's going to be W plus something that depends on theta, on this constant.
And the other question is, what is omega n for the model that you showed at the end? Which order?
You mean for these parametrizations? We were not considering omega n as a parameter, as a free parameter here, I mean. But yes, we were just parameterizing the Hubble parameter in the sense that you are able to recover at some point dark matter dominated, or let us say pressureless dominated fluid universe. But we were not considering, but we were not considering omega n as a free parameter.
But you can say, I mean, at present, what would be the amount of dark matter in this kind of model?
On this kind of unit, we should calculate it.
You don't
No, because you have to give a, I mean, in order to calculate this, you have to give a theoretical model, because this is not, I mean, these models are not based in any theoretical background, are just parameterization of the Hubble parameter as a function of time that, well, you may integrate and give the same function in terms of the redshift, but this is not based on any theoretical background. In order to get the omega n, you need to have a theory behind.
Well, as it's also built on the past, you should cover dominance of dark matter.
Yeah, well, that's why we propose this kind of models, because if you look at this term basically is going to behave as a dark matter dominated universe when this is small, and the same happens in all the four models.
Question? Yeah. I just didn't follow one of the data sets you were using for your MCMC.
Well, the Hubble parameters values provided by Moresco, the 4 points provided by Blake, where you use basically the distortion parameter and the supernova data by Union 2.1.
When you calculate your distances, are you doing that in a model?
Sorry?
When you calculating your distances, are you using that? Are you doing that in a model independent way to test the model?
Yeah, you just substitute this model.
You just substitute.
Yeah, you just calculate the H and substitute the model.
Yeah. So.
Any more questions? Okay. Now let's time here again.